Good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Professor Gabriele Sadowski. Professor Sadowski obtained her PhD in chemical engineering in 1991 at the THLM, and she's currently a professor at the Dortmund University in Germany. Professor Sadowski's research focuses on the study of thermodynamic properties of complex systems with emphasis in pharmaceutical formulations and molecules. Once again, thank you so much for accepting our invitation, Professor Sadowski. It's a pleasure to have you here with us, and please feel free to start your presentation.
So thank you very much for inviting me. And I would like to share something what we did over the last, I would say, 10 years about thermodynamics for tailoring crystallization, particularly of pharmaceutical, but not exclusively of pharmaceutical compounds. I will concentrate on 4 different subjects, so to say. First on crystalline solids, neutral ones, then on salt, because salts are very important because the solubility of pharmaceuticals usually is quite low in water, and that's why salts are preferred, and I will tell a bit about this. I will tell about co-crystals and then about different polymorphs and solvates, including hydrates, and also about a combination of co-crystals and hydrates. So these are the 4 subjects I want to cover, and I will start with the easiest one, and this is crystalline solids. So if we want to know how can we crystallize a crystalline solid out of a solution, we of course have to know what the solubility is, particularly also at function of temperature. And for that purpose, we have this very simple equation, which is a simplified version of what we are all usually using. And it's interesting because it tells us what the solubility, which is the property on the left-hand side, mole fraction solubility of component I in a liquid, depends on. And if we look on the right-hand side, we see it depends on the melting properties, namely the melting temperature and the melting enthalpy of the component we want to crystallize. And of course, it depends on temperature. This is the other property we have on the right-hand side of this equation. So that means everything here in this gray circle only depends on the solute, that's the component we want to crystallize, and depends on temperature. It does not depend on a solvent. So that means we know, obviously, that solubility is a function of both the solute, temperature, and of course of the solvent. And the only property where the solvent goes into this equation is the activity coefficient. That's the activity coefficient of the solute, which of course depend on what the rest in the liquid is, so the solvent or whatever we have in that mixture. So that means this is what we really have to know. Sometimes people say, oh, let's forget about the activity coefficient. Usually it's mainly something in the range of 1, but we can easily understand from that equation that if we would neglect the activity coefficient, it would mean that solubility is only a function of the solute and on temperature, but does not depend on a solvent. So meaning a solute would have the same solubility in whatever the solvent is, and this is obviously not true. So that means what we mainly focus on is getting this property, this activity coefficient, as function, of course, of temperature and of solvent or solvent composition or whatever we have in a mixture. And usually we take the melting properties from experimental DSC data, for example. So how do we get this activity coefficient of the solute? This is what we need a thermodynamic model for. The model we are using is PC-SAFT. This calculates the Helmholtz energy of a system as function of different contributions. It's the hard chain contribution that accounts for the volume of the molecules. Then we have a contribution that considers the attractive interactions between the molecules. And once we would only have these 2 contributions, we could describe all molecules that don't have very specific interaction forces. Then we have the A in PCSAF means association. This is based on Wertheim theory, and that accounts for hydrogen bonding. So if we add this, we can describe molecules that do form hydrogen bonds, and I have given some examples of those here. Then there are other contributions, for example, dipole and quadrupole contributions, and this is what we, for example, need for those type of components. And that means once we have, depending on what the molecules are, whether they do form hydrogen bonds, yes or no, whether they have a dipole moment, yes or no, we can switch on and switch off these contributions and describe what the Helmholtz energy of the whole system is. And this allows us then to derive any other thermodynamic properties we might be interested in, for example, activity coefficients, and by that solubilities. We need different parameters for that. So we need the size of the molecules. For that, we have the segment number. So how many segments do we have? We have the size of the segment diameter. We have a parameter telling us what the attractive energy between two molecules is. And for association, we have the number of association sites and the association strength and volume. And if we have a dipolar molecule, we need to know what the dipole moment is. So the nice thing is we do have these parameters available already, obtained by us and also by other groups worldwide. So they are available now for more than 500 substances, including more than 100 organic solvents, more than 40 polymers and any copolymers thereof, and also for quite a number of APIs. API stands for active pharmaceutical ingredients. This is the pure component parameters, and if we have more than one component in the system, that's what we obviously usually have, then we need for any binary an additional binary parameter, and we have those binary parameters already for more than 1,000 mixtures. So the nice thing is once we have those parameters in our database, we can then go on and calculate, for example, activity coefficients and solubilities. And this is what I want to show you. I will now show you the outcome of those type of modeling. We start with a solubility of a compound in a pure solvent. So this is the easiest thing to do. You see an example here. This is ibuprofen, which is, as we all know, a pharmaceutical, and its solubility in acetone. And we know that solubility increases with temperature, and this is what we see here. This is a molecule, ibuprofen, and this is a solubility data. And usually we determine the parameters of the API, which is ibuprofen in this case, by fitting to these solubility data. So we have to do this because usually we would like to fit those parameters to vapor pressures and liquid densities. But if we talk about pharmaceutical compounds, they are crystalline solids in a pure state. So we don't have vapor pressures, neither liquid densities. And for that reason, we usually take solubility data to fit the API parameters together with the binary parameter. So that means we get a nice correlation. This is what you see here. It's not a prediction, it's a correlation. And obviously we have quite a number of parameters. This fits very nice. But the achievement is not to describe these data. The achievement is to get the parameters and then to use these parameters to calculate something else. For example, the solubility in solvent mixtures. And this is what you see here. This example is this time paracetamol in a mixture of water acetone. And what you see here on the x-axis is the water mass fraction in the solvent mixture. So we have on the right-hand side the solubility of paracetamol in pure water. On the left-hand side, we have the solubility of paracetamol in pure acetone, which is much higher. So water, unfortunately, is a dead solvent for most pharmaceutical compounds. And we have been asked, so how can the company ask us, we have this point, that's solubility in acetone, what do we need to add to acetone to increase the solubility? And so what we did is we took our parameters and we calculated the solubility in acetone mixtures. So adding a second solvent and then asking ourselves, what will be the solubility in that solvent mixture? And as you see, what we got is we got a solubility increase in this in acetone by adding what the pharmacists are calling a non-solvent. So they said it's a totally crazy idea to increase the solubility in a solvent by adding a solvent, which is obviously a non-solvent for that API. But as you can see, it worked. So the line this time is a pure prediction, and the experimental data were estimated afterwards, and they very nicely fit the experimental data and the modeling. And that means indeed, and quite often, particularly in water-containing systems, we do have a maximum in solubility compared to solubilities of both solvents. So this is really a prediction. So that's so to say the easy part. Solubility of crystalline solids, we need the melting properties, and we usually use those data for correlating purposes by fitting the binary parameter. The interesting part is then how can we improve the solubility in water? As you have seen on the previous slide, solubility in water is usually quite low. And of course, that's bad, particularly for pharmaceutical components, because we take the components and we want, of course, them to be dissolved in the body and to take or to make their job. And as solubility is quite low, forming a pharmaceutical salt is quite an alternative. So how does this work? So that's the solubility of an API at constant temperature, but this time as function of pH. And quite a number of APIs are able to dissociate. If we have an acid-based API, it can release a proton, and then we get a charged API that's released a proton. And this is determined by the dissociation equilibrium of that API in water. And this is described by the so-called pKa constant, which is the dissociation constant of this equilibrium. And this is known, usually for pharmaceutical compounds, it's always known or have to be known, otherwise those components cannot be brought on the market, and there are possibilities to determine this constant. And that's what you see here, this API releases a proton. That means if it releases a proton, pH will decrease by releasing a proton. That means that once we know what the concentration of the protons in a system is, we immediately know what pH is. And this is what you see here. This is what we call pH API. So if I take just the API, put it in water at a certain temperature, then it has a certain solubility. This is what I can find here on the y-axis. And it also will have a certain pH. So this is what we call the intrinsic solubility. So just at the pH that forms itself by taking the API and dissolving it in water. This pH can, of course, now also be changed. So what we do see is if we increase pH for an acid component, so this equilibrium is shifted to the right-hand side. So that means that our API is more and more dissociating in the better soluble API minus form. And so solubility is increasing if we have an acidic API when increasing pH. But of course, pH doesn't change itself. So we have to add another component to change pH. To increase pH, we would need a base, for example, sodium hydroxide. To decrease pH, it needs an acid, obviously, for example, HCl. So what, and in the body, by the way, we are usually very acidic. So in the body, pH is usually very low. In the gastrointestinal tract, it might, or in the stomach, it might be about 1 or 2. This is very, very much smaller than 7. In this case, where we have an acidic compound, by increasing pH, means by adding NaOH, we can increase the solubility because we do form more and more of the charged form of the API. Doing this, we obviously add not only OH minus, but we also do add Na plus. So we add sodium ions to go right in this diagram to increase pH. And that means we do have now also an equilibrium between the API minus and the cut ion of the base we use to increase pH. And that means these two compounds, they may form a salt. And of course, this salt is described by the blue box. So we need so it has a certain solubility product. And if we are at very high pH, meaning we have a high concentration of sodium plus, we might even reach the solubility of the salt. So, and this is what we see here. Above a certain concentration, now the salt is precipitating. And usually the salt, of course, has a different solubility than the non-ionized form. And at very high salt concentrations, of course, the salt will precipitate. And that means we now have two solubility lines which cross each other. We have the red solubility line, which is the API solubility. And if we have an amount of Na plus in a system that is high enough, the salt will precipitate. And this is what we get here. So we will then see really a cut in solubility, and blue and red means that the solid formed is different. For the red line, it's the API that's crystallizing, and for the blue line, it's the API salt that's crystallizing. And its solubility is described by this so-called solubility product. This is what we have here. It looks like this. So we have solubility product, which is a thermodynamic constant. It's nothing else than activity of the two ions, meaning that we have the concentration of the anions, which is, of course, equal to the one of the cut ions, times the correlating or the corresponding activity coefficients. So that means for describing these curves, we need the solubility of the API. We need the pKa value of the API, which is usually known. And of course, also we need the solubility product of the salt. And then we can describe the solubility as function of pH, accounting for the fact that we do have at least two species that might crystallize in that system. I will show you an example first for experimental data. This is the solubility of thiabendazole. I always show you how the molecule looks like. This is this molecule. And as you can easily see, this is an acid. Sorry, this is a base. This is a basic molecule. So that means we do have now the fact that we at a high pH, we have the thiabendazole molecule crystallizing. At low pH, we get the salt, which is formed by using the counter ion of the acid. So once we use phosphor acid to decrease pH, we get the phosphate of this salt, which is crystallizing here. And of course, if we do use a different acid to decrease pH, we get the corresponding salts, and these salts have different solubilities, which is not surprising, but one has to understand that that happens. So this is the phosphate that forms, and this is the chloride of thiabendazole that forms. And for the non-ionized form, you see all curves really match on one curves, and of course the ones for the salts are different. We do not have the solubility of the acetate here, but this is obviously something which we would have to expect in between. So that means, of course, it's not surprising, the solubility of the ionized form, that means of the salt, of course, depends on the kind of acid or base that we used for shifting the pH. And this can now, once we know this and understood that that happens, we can also, of course, model this. So for that, we use an extended version of PCSAFT, where we also have an extra contributions to account for the charges. Using this, we can describe small electrolytes, sodium chloride, for example, but the same contribution can also be used to describe the ionized forms of any molecule of an API, for example. And this is results I've shown you, or I show you from a recent paper from this year. So we have 4 different molecules. This is naproxen, this is ibuprofen, this is lidocaine, and this is terfenadine. So these are 4 pharmaceutical compounds, and you just get an impression how complex they look like. And the data you see are data from literature. And the notation is the following. We have always pH on the x-axis. So you do see that we have acidic compounds, naproxen and ibuprofen, which have a solubility increase once we go to higher pH. And we have the 2 components here on the bottom, terfenadine and lidocaine. They are basic, so their solubility is increasing once we decrease pH. When you see filled symbols, that means that the experimentalists investigated the crystal form they observed by pXRD, which is a very good idea. So as we expect to have at least 2 different solid forms, it makes a lot of sense not only to analyze what the liquid composition is, but also what kind of solid we have, or they had. Filled symbols mean they analyzed the solid, and this is the API, as the non-charged API, and empty symbols mean that this is the salt that was precipitating. This here, and also here, this was the lidocaine salt. If we have half-filled symbols, that means that the experimentalist did not investigate what the solid form was. I don't know why, maybe they didn't expect to have different forms, but as we just look here at the picture, we can assume that this is the non-charged API, whereas these 2 might certainly belong to the terfenadine salt. So we took these data and applied the modeling, that means activity coefficients, and also accounting for the dissociation equilibrium and for the solubility product of the salt. And this is what we got. The red lines mean that this was what we modeled for the API of the non-charged molecules. And blue lines mean this is what we get, assuming that the salts are precipitating. And as you can see, this very nicely fits that we assume, or that the experimentalist found non-charged solid precipitating until about this point, and at very high pH, the transformation to the API salt. And we also predicted the transition between the non-charged solid and the salt for the experimentalists, or for the experiments where we don't have the experimental proof, but we are sure that this makes quite a lot of sense. So that means our message is, if you have a molecule that is able to dissociate, attract, or release protons, and the solubility is the one in water, always also consider investigating what the solid form is, and then, of course, use the solubility of that particular solid. So this brings me to co-crystals. What is a co-crystal? A co-crystal is a crystal that is built up of 2 different molecules. So we have an API, they are pharmaceutical compound, and they very often have a very low solubility. Co-crystals are built of API molecules and co-former molecules, and they build a common crystal lattice. This crystal lattice is less stable than the one of the pure API, and so it will better dissolve. It has a higher solubility, but more importantly, it is faster dissolving. And the nice thing is, once you have formulated a co-crystal and you take it and dissolve it in water, in a body, for example, you get the dissolved API molecules back. You also get the dissolved co-former molecules. So, of course, for pharmaceutical applications, co-formers are usually taken as being molecules that we are able to eat, or that we can eat, so no poisonous molecules that form together with the target molecule API, a common crystal lattice. And there's a lot of work going on. How do we find the right co-former for a given API? And even more important, how do we produce this? And this is not an easy task. So we go to the right-hand side to the triangle here. So we have the triangle, meaning that we have the API here at the bottom right corner. The co-former is in the left corner. And then these two compounds, which are both solid in pure state, are dissolved in a common solvent. And then you get a solution here. And then from that solution, water is, if this is water or whatever the solvent is released. And then we hope to end up here in the co-crystal region. Because as you see, we do have different solids here. We have the API that might crystallize. We have the co-former that might crystallize. And they usually form a co-crystal in a stoichiometric ratio, which is a 1-to-1 ratio. So that means just in between the API and the co-former, we have here at the bottom line in a solvent-free system, the 1-to-1 co-crystal. So we have a system where we can expect to have 3 different solid states. And all of them have in this solvent here a different solubility. So we have different regions. This region is where we get the pure API, which is then in equilibrium with the solution along that solubility line. If we are in this region, we get the pure co-former crystal in equilibrium with its saturated solution. And we don't want to be here and there. We would like to have the co-crystal. And that means this co-crystal, this triangle, once we are here, we get the pure co-crystal in equilibrium with its saturated solution. And in between, we have 2 3-phase regions where we get both co-crystal and co-former crystals next to each other in equilibrium with this solution. And in this white triangle, we would get API crystals together with co-crystals and that saturated solution. For people who want to have a co-crystal, they want to be here in this triangle. They want to be a co-crystal only and not API crystal nor co-former crystals. So what people usually do is they prepare, if they want to have a 1-to-1 co-crystal, they say, okay, if we want to have a 1-to-1 co-crystal, we take the co-former and the API in a 1-to-1 ratio, and we dissolve them in a solvent. And once you do that, you end up here. So along this arrow, you would move having a 1-to-1 solution of these 2 components. And then evaporating the solvent would bring you down here, and you would end up in this white triangle. That means you would get indeed co-crystals, but they would be in a mixture together with API crystal. And this is not what you want to have. To end up here and to get the pure 1-to-1 co-crystal, you would have to start from a solution which would have to contain more co-former than the API, and only then you would end up getting here in a region where you really could crystallize a pure 1-to-1 co-crystal. So this is really not intuitive, but for that, you really need to know what the phase diagram is. So, and this is where we come in. So thermodynamics is calculating and understanding those phase diagrams. So what do? We first are interested in getting the solubility of the API in the solvent co-former mixture. So this is this blue line here. And we are interested in this line. This is the solubility of the co-former in a solvent and in presence of the API. This is this blue line. And for these blue lines, we use the equation we already have. So this would be the melting properties of either API or co-former. This would be the activity coefficient, again, of that molecule in the solvent, but in presence of the other component. So this would bring us to this blue lines. We are, of course, also interested in to know, or most interested in to know where the green line is. And for the green line, for the solubility of the co-crystal, we can unfortunately not apply this equation. And the reason is that we do need the melting properties, the melting temperature and the melting enthalpy of the solid, which is the co-crystal. But the co-crystal doesn't exist in a liquid. As you can see here, as soon as the co-crystal is dissolved, we don't have a co-crystal molecule anymore, but we have a mixture of API and coformer. The co-crystal only exists in a solid state. And that means there is no melting temperature nor melting enthalpy of a co-crystal. And that means we cannot apply this equation anymore to get the green line. So to get this, we assume that this is like a salt formation. We have two species, this time not the anion and the cation, but the API and a coformer. In a certain stoichiometric ratio, in this picture 1:1, they form a co-crystal. And this can then be described again by this equilibrium constant. And this is, again, a solubility product. This is the same idea as we apply for the solubility of salts. And we have here the stoichiometric coefficients. So this is 1:1, but can also be 1:2 or 2:1 or whatever the stoichiometric ratio is. So what we do is we need one single point of this green line in any solvent, because the nice thing is that the solubility product does not depend on a solvent. It only depends on the solid, on the solute. So once we have a solubility point, one solubility point in any solvent, we calculate solubility is X, and we calculate the activity coefficients, and then we can determine what the solubility product is. And this is a property that belongs to this co-crystal. And once we have this, we can then turn the equation around. And then for this particular fixed and constant solubility product, calculate the solubility in any other solvent, because in any other solvent, we will have different activity coefficients. And that brings us to different concentrations, solubilities. And I will show you an example how this works. This is a co-crystal of carbamazepine and nicotinamide as coformer. And the solvent where we found the experimental data is ethanol in this case. And you see the green line is the solubility of carbamazepine in ethanol, the orange one of nicotinamide in ethanol, and the gray line is the co-crystal. And this is what we used to determine the solubility product of this co-crystal. And then we predicted, and that's really a prediction, what would happen using this KSP solubility product determined from the left-hand diagram. What would happen if we then exchange the solvent? That means go from ethanol to ethyl acetate. And what you see on a very or what you immediately see is the picture is completely different. As the x-axis is the same, so it's still carbamazepine and nicotinamide, but the solvent is different, and also the whole picture looks different. This is a total prediction, and then we also found experimental data, and they very nicely fit. So if somebody wants to produce a co-crystal, he or she is, of course, interested in to get a huge area, a huge process window where one obtains as a co-crystal. And for that, you can easily see that on the left-hand side, I mean, despite of the fact that the axis is not totally identical, but this makes things even more clear, so that the process window on the left-hand side is much bigger than on the right-hand side. So that means if somebody says, I would like to produce a carbamazepine nicotinamide co-crystal, we could suggest, based on thermodynamic modeling, which solvent to use to really have a process, a comfortable process window to really obtain and produce this co-crystal. This is a picture of succinic acid nicotinamide. They form a 2-to-1 co-crystal. So nicotinamide, 2 nicotinamide molecules, or the ratio is 2 nicotinamides and 1 succinic acid molecule. They form a common co-crystal. And what you see is that we also do have the pH influence. So this time we have pH on the x-axis. And as I have shown you, solubility of the pure solutes in a common solvent, this time water, depends on pH. So you see here we have nicotinamide, which is obviously a basic molecule. At a certain low pH forms salt, which has its own solubility. And for the succinic acid, it's even worse. So you see that we have succinic acid is, this is an acid, as the name says, succinic acid. So we have at low pH the succinic acid molecule, the neutral one that crystallizes. Then we have succinic acid salts at higher pH, and at even higher pH we have a salt hydrate formation, but I will come back to this. So we have 3 different solid forms for succinic acids as function of pH, and we have 2 different solid forms for nicotinamide as function of pH. So this gives us an additional property in hand that we can use for designing our crystal process out of water. And if we want to go to high pH, we then add sodium hydroxide, and going to lower pH, this would mean we would have to add an acid, for example, HCl. So this is a solvent here on top. And we have succinic acid here on the lower left, and nicotinamide goes to the right. And now we keep the temperature constant and we change pH. So at pH 4, we are here, you see pH 4. So we get for the nicotinamide, the neutral molecule, and also for the succinic acid, we would get the neutral molecule. And this is what you see here. This is the solubility of succinic acid at that pH, and the green dot is the solubility of nicotinamide. And by doing the same, or by applying the same approach as before, we get the co-crystal line, which is the gray one, and which very nicely fits to the experimental data. So this black dots are solubility of the co-crystal as in water as function of concentration. So that's about pH 4. What happens if we then change pH? For example, we go to a pH close to 6. So we move to the right in the 2 diagrams. So that means we still have the neutral form of nicotinamide, but now we have not the succinic acid anymore, but now we have the succinic acid salt. So that means if we look to the right, this was the solubility of nicotinamide before. It is now decreased, as we can see. So we are now here at pH almost 6. And the solubility of the succinic acid neutral form in salt is almost the same as the 2 different pHs. So we are still here more or less at the same point. But for the co-crystal of the 2, it's now totally different. You see that we got a different picture here. And this also nicely fits the measured experimental data. And going to a very low pH, for example, pH of 2, brings us to the left side, where we have, again, the succinic acid, the neutral form, but the nicotinamide salt. So we again move to different points in the left right-hand side diagram. And the gray line, that is the one we are interested in, because this is where we get the co-crystals. An equilibrium-limited solution also, again, looks quite different, but still very nicely fits the experimental data. So that means we are able to say how the picture depends on temperature, on the solvent, and also on pH. And then depending on what you would like to get, or how big the process window should be, you can influence temperature or pH to get most conveniently the co-crystals you are interested in. Now I move to the last part, which is polymorphs and solvates. So what is a polymorph? APIs we are talking about, the molecules, you have seen already some examples that are used for pharmaceutical applications, are quite complex molecules. And they usually can not only form one type of crystal lattice, but they can form different crystal lattices, so different solids, crystalline solids. And this is what called polymorphs. So that means once we have a normal API, so we have an API in water, for example, then we get the normal eutectic diagram. On the left-hand side, where we have pure water, we get the melting point of water, which is, as we all know, 0 degrees centigrade. On the right-hand side, we have the melting point of the API, which is usually much higher than normal ambient temperature, which is quite high. And then we get, I would say, normal eutectic system. And we have the eutectic point here. And that means everything here on the right-hand side, meaning right of the solubility line of the API, would bring us to pure API crystals. So this is what we have here of a particular crystal form, which is what we have here. If we then might also have a co-crystal formation between water and API. So this is nothing else as a co-crystal. A hydrate might form. So again, the water molecules and the API, they form a common crystal lattice, which I would call a co-crystal. Usually people don't call it co-crystal, they call it a hydrate. The reason is that usually the term co-crystal is used for two components that are solid at ambient conditions. And as we know, at ambient conditions, water is not solid, but still the idea is exactly the same. They form in a stoichiometric ratio common crystal lattice. So we have, again, three different solids. We have the water on the left-hand side, API crystals on the right-hand side. And if they form a one-to-one co-crystal or hydrate, then we have here, just in the middle of this diagram, the third component that might crystallize, and that's the hydrate. And that divides our diagram now in, we have the hydrate. On the left-hand side, we have the hydrate solubility, which is the blue line. Still the water solubility in the API. Below the eutectic, we have a mixture of water crystals and hydrate crystals. On the right-hand side, we have an equilibrium between the hydrate crystals and API crystals. And above a certain temperature, we then don't have the hydrate anymore, but we get API crystals. And then if we have more than one chances for the API to crystallize in the pure state, we might still have another polymorph of the API, which has a different melting temperature. So for example, this is form 2, whereas we before had form 1. So this was, so to say, the old melting temperature, or the first one I've shown you for the form 1. A different crystal will have a different melting temperature. For example, this one, if it's higher, form 2. And then we have a region where we get crystals of API in crystal form 1. And we have another region at higher temperatures where the most stable form is the form 2. So we get a different crystal form. So this is a quite nice diagram. And as you see, depending on temperature, we get API hydrates, API in crystal form 1, and API in crystal form 2. And this is interesting for pharmaceutical applications because as these forms have different melting temperatures, they also have different solubilities. And as I also already said at the beginning, solubility is really an issue. So we do have 3 different solids here, the hydrate, API form 1, API form 2. But the nice thing is, once we have them dissolved in water, they all look the same. So that means for the liquid, and this is where our model comes in, our activity coefficient model, it doesn't change. So the liquid always looks the same. We can apply our model to any of these forms. The only thing that's changing is the left-hand side, so the melting properties of the API, or we need to know what's the solubility product of the hydrate is. And this is what we have here, and we do apply our activity coefficient model to get the activity coefficients and that also the solubilities in all that cases. So I will show you an example. This is carbamazepine, and carbamazepine is what we have on the right-hand side here. On the left-hand side is water. Forms 2, not only 2, but what you see is is form 1 and 3, two different polymorphs having different melting temperatures. This is form 1 here, and at low temperatures we have carbamazepine form 3 crystallizing. And on top of this, it also forms hydrates. So that means at low temperatures, the hydrate is more stable than the carbamazepine form 3, but still we could find experimental data for the thermodynamic stable hydrate, but also for the anhydrate of form 3, which is thermodynamically metastable. But this helps us to really prove that we do correct. So we do the same calculation for the two forms just by exchanging the melting properties, and for form 1 and form 3. And for the hydrate, we need to know what the solubility product of the hydrate is. And this again looks quite the same as for the salts or for the co-crystals, because it's always the same approach. So we have here the carbamazepine concentration and activity coefficient, and here we have, as it forms a hydrate, water concentration and water activity coefficient. And as it forms a 1:2 hydrate, we have the stoichiometric coefficients 1 and 2, and this gives us a solubility product of the hydrate. And in particular, we see that we have X water times gamma water. And you certainly know that this is nothing else than relative humidity if this solution is in equilibrium with a humid air. So this is water activity, and this is actually the same as partial pressure of water divided by vapor pressure of water. And that means once your system, liquid system, is in equilibrium with a humid air, the humid air determines RH, the relative humidity of that air determines RH, and that means it determines what the solubility of the hydrate is once we have a fixed K value. So that means hydrate formation depends, of course, on this kind of solute, whether I have carbamazepine or something else. It depends on temperature, and it depends on RH. Important thing is, you can change the composition in a liquid, but this doesn't really help, because the liquid, as soon as it is in equilibrium with humid air, the relative humidity of the air will translate into this term, into the activity of water here, and this determines whether you get a hydrate, yes or no. And I will show you in the next diagram what this means. This is the same substance, carbamazepine, and this is carbamazepine 1 at high temperatures or at low RH. I go once back. At high temperatures, I get the anhydrate or at low pH values, which means low water compositions in a liquid. And this is what you actually see here. If I want to get the anhydrate, I have to go to high temperatures and or low RH. And then there's a transition between this anhydrate and the dehydrate, which is determined by this experimental data. And you can determine this using the pure carbamazepine. And this line is then fixed and tells you once you have temperature fixed and RH fixed, you are here or there, and this is what you then only have to, let's say, consider. That means if I'm at room temperature, that means a little bit below 300 Kelvin, there's a critical RH of 62. Above this RH, you will get dehydrate, whatever you do. And below this, you are safe if you would like to get the anhydrate. And this does not depend on the components that you also additionally have in the liquid. So for example, if we have carbamazepine dissolved in a polymer, we still have the anhydrate crystallization at low RH and the dehydrate crystallization at high RH. And what the RH is just determined by this diagram, which did not know anything about the polymer as a solvent at all. So we are at 25 degrees centigrade. So we are, as I already said, at about 62 RH. And that means this RH determined by the just knowing what the carbamazepine does, also determines in a mixture with PVP, where we do have the transition between anhydrate and dehydrate crystallization. What does it tell you? For people who make pharmaceutical compounds, they have to make sure that their compound they are producing is stable. So if they want to sell the anhydrate, it is most important for them to know this critical RH, because whatever they do and whatever they add to the liquid, it doesn't matter. As soon as they are above 62, they get the dihydrate, and this is not what they want. And the same is just to show you, if you have a different polymer, picture is changing a bit, concentration as a solubility is changing, but what is not changing is the transition between the anhydrate and the dehydrate. It stays what it is and what it already was for the polymer-free system. So hydrate formation is controlled by RH. Whether we do get hydrates, yes or no, is only a question of RH. And if I want to have the anhydrate, I have to make sure that whatever I have stays below the critical RH. And now, this is my last and favorite example. We can now imagine that we want to build a co-crystal, but our co-crystal former and API also might be able to form hydrates. So that is, let's say, this is very interesting what happens then. So this is a picture we already had, I've shown you. So we are at a temperature here in a right-hand side diagram where we are above hydrate formation. So that means the only interesting point is this green point, which is the solubility of form 1. And this is what we have here. If we now change temperature, decrease temperature in the system, and the solubility, solvent is water, you see that we have two different solids. We have the hydrate, which we have here. Solubility of the hydrate, and then we have the transition between the hydrate and API1. So the left-hand diagram is changing. On this side, we have the transition between the API and the hydrate, and we have the solubility of the hydrate. This really immediately translates from this diagram into the right-hand side diagram and makes the picture a bit more complex than before. If we are unlucky, also the co-former might form hydrates. And if we are at a temperature where at that same temperature, where also the co-former might form a hydrate, we have the similar picture what we have for the API, also for the co-former. So that means we do also have here solubility of the hydrate, and we have solubility, or not the transition between the hydrate and the co-former anhydrate at that point. And we still want to get the co-crystal. What you could see is the co-crystal region becomes smaller, unfortunately, if co-former and or API may form hydrate. And on top, sometimes even the co-crystal may form hydrates. So that means we have a co-crystal consisting of two components of co-former, API, and water. And then the picture looks like this. So that means this is the most complex system we considered so far. Still, we want to be here. We want to get the co-crystal. What people do is they take the common water as a common solvent. They dissolve the co-former and the API in a certain ratio and at a certain concentration. For example, at that concentration, which brings us in a homogeneous solution, no crystals. And now you can imagine that it depends on the ratio between the co-former and the API at that concentration, what kind of solvent or of solid crystal you get. For example, if you are on a very right, so you have more APIs in co-former, you get the API hydrate. That's not what you want to have. If you go to a little bit to the left, so have a little bit an increasing amount of the co-former, you end up here and you get the co-crystal hydrate. This is also not what you would like to have. adding a bit more co-former brings you more to the left. So this time you would end up here in the co-crystal region. But if you add too much co-former, you end up here. You get the co-former hydrates. This is, again, not what you want to have. And you see here that the difference between the compositions is not quite big. So that means if you want to know, and if you are interested in to know the concentration here, you have to use as an initial solution in water to get the co-crystal. You really have to understand what the phase diagram is. Otherwise, you get wrong, and you get a solid you never want to have. And that's why the PhD student I had, so Linda Langes, she did this calculation for theophylline and citric acid. These are the diagrams of water and both of the components, for theophylline on the top and citric acid on the bottom. And this is what she got. So she got 4 lines. This is the solubility of the pure theophylline. On the right, on the very left, we have the solubility of the pure citric acid in a mixture of water and theophylline. And this gray line is, only the gray line is the one where you get pure crystal formation. And to the right, you have the area, you have the area where you get the pure co-crystal hydrates. This is what you do not want to have. So this is the area to be once we are interested in getting pure co-crystals. So this is just, I wanted to give you an impression of what can happen, and that solubility is not just a data point. So the take-home message is solubility sounds quite obvious, depends on, of course, the kind of solute. So what do I want to dissolve? On a solvent I want to use to dissolve it, and on temperature. So that sounds trivial and obvious. The thing is this one, kind of solute. Solute is not just the crystalline solid. It might be the crystalline solid, but it also might be an amorphous solid, which I skipped here. It might crystallize in different polymorphs. It might form salts. It might form co-crystals. It might form solvates and hydrates. So this is what you have to know. You have to know, obviously, what the solute or what the crystal form is, but this also depends, again, on solvent and temperature. And that makes things not trivial at all. So that means once we want to crystallize and we want to have a particular solid crystal, we do not really have to know what the solubility is, but we really have to understand the phase behavior. And that's nice because we are thermodynamicists, and that is what we are trained to. This is my take-home message. And with this, I like my group. So that's my group. Photo was taken this week. And we are also grateful to our sponsors. And I thank you very much for your attention.